Hello, students. Hello, students. We will today see the limitations of the algorithm power. So when you say it as the limitations of algorithm power, we have already seen that we have different ways, that is the different ways are nothing but we have seen with the lower bound arguments. We have also seen with the adversary arguments, that is information theoretic arguments. We have also dealt with the we have also seen with the various possibilities. Okay, so the problem reduction, once when you are taking it, we are going to see with the classification of various problems. The classification of the problems are emerging with different types of problems. So as I told you, when you start up with an algorithm, we will be first designing an algorithm, and we will be seeing how it can be found out by for its efficiency. So their problem, if you see, we will be first checking whether it is a tractable problem. So if is there any polynomial time algorithm that can be solving it? So the possible answers are yes and no. So there will be some problems where you will be having a polynomial time algorithms. There will be some problems which doesn't have the polynomial. So we require some exponential time complexity. So how to classify is basically we use the help of the reduction one. So when you say it as reduction, so there are two different types of problems. One is your optimization problems, and another one is called as the decision problems. So when you talk about the optimization problem, we have seen some problems earlier in our introduction, or in brute force method, where or in even in dynamic programming we have seen the knapsack problem, traveling salesperson problem. Basically all these problems are considered to be the optimization problem. Now if you see, the traveling salesperson only can be changed to as a decision problem. How it is we are not going to consider the cost of it, the weights. Okay, if you have a non-weighted graph for the same traveling salesperson problem, with the same graph we can also find out the Hamiltonian circuit, whether there exists a path from which forms a simple path or a simple cycle, where it starts with a city, ends with a city, and by covering all the intermediate cities or the vertices. So optimization problem, usually we will be finding a solution that is going to maximize or minimize some objective function. For example, in knapsack problem, we have certain objective functions. We will be having a knapsack. We have to find out the best fit, or without exceeding the knapsack capacity, how you can choose the items in such a way that it gives a maximum solution profit. Decision problems, usually it will be like yes or no questions. Like previously we have seen the decision tree, where we, if you want to sort some three elements by using the insertion sorting, we can use the decision tree structure or the decision problem, which gives you a value as yes or no. So many problems have decision as well as the optimization versions. So the optimization version means you are finding a Hamiltonian circuit of minimum length is your traveling salesperson problem, that is an optimization. Finding the Hamiltonian cycle alone is nothing but it is a decision problem. So decision problem are usually more convenient for finding what is the complexity, how we can solve it, what is the output which is going to be generated or obtained for a particular problem. So we have something called as a class B problem. Basically, what is this class B problem? Any problem, it is a deterministic algorithm, isn't it? So when you say it as a deterministic, it can be a deterministic algorithm or a non-deterministic algorithm, where you will be saying it as whether it is a polynomial or it is a exponential form. So here, a class B problem, usually it will be a polynomial one. The class of decision problems that are solvable in order of P of n of time, where P of n is nothing but it is a polynomial of problems input size n. So searching an array, when there are n elements, you give a key value to search element uniqueness. If you have an array given list of numbers, n numbers, you want to find how many numbers are unique in that. The graph connectivity, graph acyclicity, all these comes under the polynomial time. Okay, so class NP is nothing but the non-deterministic polynomial, where you will be having a class of decision problems whose proposed solution can be verified in the polynomial time, which will be always equal to solvable by a non-deterministic polynomial algorithm. So when you say it as the non-deterministic, it is a two-stage procedure where you will be having the guessing stage as well as you will be having the verification stage. When you say it as the guessing stage, if you consider an arbitrary string S, it will be generated, which we can think of as a guess at a solution for the given instance. Verification means, for example, a deterministic algorithm is given. We need to check whether the solution is going to be correct. So for an algorithm, it takes both I and S as its input and check if S is a solution to the instance I. So when you say it as the computational complexity, we go for the NP problem with the basically with the problem that which it can be checked. So if the problem returns yes or no based on a decision, then we will be saying how quickly we can get the time factor. So here, when you say it as the time factor, we are going to do it with the help of the satisfiability norm. So when you say it as the satisfiability norm, how we are going to identify it? The values are going to be identified based on whether you have a decision problem, whether it is NP complete or not. So if you have a Boolean expression, when it is in a conjunctive normal form, you will be seeing whether those values are being satisfiable. So every problem in the NP will be having a polynomial time which is reducible to D. So this product or a problem is called as the non-deterministic algorithm, where you will be guessing for a truth assignment and see whether D is in NP or not. And every problem, if you consider informally, any problem if you take, because by definition we would have defined it in some way, but when you go for the NP, it can be reduced to it in polynomial time factor, where you will be guessing a truth assignment. So when you say it as the truth table, for example, you have something called as the conjunctive normal form and the disjunctive normal form. So when you say it as the conjunctive normal form, there will be various literals or a clause will be given, or a formula will be given. So from that, you have to literal means it's nothing but you are saying it as A or A not. When you say it as clause, we can say it as A or B, or A and B, A not B, etc. So all these conjunctive formals, what you will be doing is you will be getting a non-deterministic algorithm where we will be saying that it has to be a guessed for a truth assignment, and substitute the values into the CNF formula to see if it is going to evaluate it to true. So for all these things, we have a checking phase where the checking phase is by default, it is given as order of n. So whenever you go for any problem, whatever problem you have to check it up based on what problems are there. They will be classified as a non-polynomial one, where you can say it as the existence of the Hamiltonian circuit, or you can say it is as a partition problem, where it will be checking whether there is any partitions to form the various disjoint subsets within the same sum or not. Or you can also go for checking for the various combinations for the combinatorial problems for an optimization problem. So here whenever you give it in the form of a CNF form, you will be having a Boolean expression where the Boolean expression needs to be evaluated. So all the problems, whatever we are giving it, it can be solved in this manner, but whenever you are going for guessing, it may not work correct. So we are saying that P is a subset of NP, but it is a big $1,000,000 question where P is equal to P or not. So based on this, we need to use the theorem for the. So here we have a theorem which is called as the Cook's theorem, where we will be doing it with the help of the assignments. So here, when you take it as the NP complete problem, it is a non-polynomial deterministic algorithm. So where every decision problem is complete if it is a hard as any other decision problems in NP. So here we will be saying it as whether D is in NP or not. So every problem in non-polynomial is polynomial time reducible, and it is to D. So we can see whether it is a complete problem, traveling salesperson problem, partition algorithm, knapsack algorithm, if graph coloring, everything we have various techniques to solve it, and we will be saying it. So every complete problems, when it is going for the time reduction, we will be seeing how it can be solved. So basically we will be doing it with the help of the two stages, that is the guessing stage and the verification stage. So yeah, eventually when it comes into picture for all the NP problems, we need to solve it, and we have to take the values, and certain cases the values will be unknown. So based on that, we will be finding it. So if at all, if there is any specific algorithm which is not given, so if you want to further analyze and find out what is the time efficiency, that can be determined with the help of the non-polynomial algorithm. So particularly in this, what we are going to see is whether we will be having it for all the computational complexity. We are going to see whether how the theory can be evolved by using these algorithms for all the different various problems. So once the problem is taken, how it is going to classify, it's basically determined for all the lower bounds. Lower bound means whenever we indicate at it as a lower bound, we should also check whether it has a trivial lower bound. How it is going to be checked is the way where when you encounter a particular problem, so where exactly what the problem is given has to be specified, and when you are specifying it, you will be getting to know what is the time complexity which is taken for that algorithm. So whether there is any algorithm exists with the same time complexity, or we have to also see, say for example, I told you before in the previous class, the problem reduction. When you talk about problem reduction, if the algorithm is very, very complicated. We need not dwell into it in deeper. So what we can do is we can convert it into another problem. For example, LCM can also be found by finding the GCD. M into n divided by GCD of m comma n gives you the LCM of two numbers. So if at all there is no known algorithm, what we will do is we will be trying either to change the data structure or to the technique or whatever in a simple manner we will be trying it only because we always aim for a efficient algorithm. The efficiency is going to be determined on based on various scenarios. So with respect to all the algorithms, we will be determining the efficiency of algorithm, which it's basically based on the asymptotic. We have in the first introduction chapter, we have seen the three asymptotic notations. So by using all those asymptotic notations, we will be determining what is the time taken. So the classes of NP complete problem is called as the NPC, where you will be using the Cook's theorem. Cook's theorem is developed in discovered in 1971, where it is the first NP complete problem which is discovered, and it is also a CNF satisfiability problem also. So to show a decision problem is NP complete, you need to show that the problem is NP, as well as you should also show that a non-NP complete problem can be transformed for the problem or to the problem in question in polynomial time. So transitivity or the polynomial reduction will come into picture. So based on that, we will be using various literals, and based on the literals, we can classify the algorithms, as well as we will be finding out what is the other measurements you have for the time complexity. So basically, when you say with the NP complete problem, the NP complete is a decision problem. So whenever you go for the decision problem, we will be seeing when a problem is given, we have to see a decision problem is whether it is NP complete. If it is as hard as any problem in NP, that we have to see. So we will be considering P as the subset of NP, where you will be seeing what is the decision problem and whether the decision problem is in NP or not. So similarly, we have to also check whether every problem in NP is going to be polynomial time reducible to D. So if at all some instances are matching, for example, we take as two instances D1 and D2, and if there is some mappings given for these instances, which helps us to identify the activities in it where with a yes or no component or something, then we can easily find out at what instances it will be reducible to find one where you will be transforming the instances. So one instance to another can be transmitted or transformed by use the polynomial time algorithm. So every algorithm, we need to find out what classification it belongs to. Based on that, we have something which is polynomial, which is NP complete, and which is also NP hard problems. So based on all these things, we need to cover the limitations. And when you say it as this NP is whether it is equal to NP. Okay, it is actually a big $1 million question which needs to be answered, where it is used for the practical implementation. So whenever you have a NP complete problem, you have to first check whether D is in DP, NP, or every problem in NP is going to be polynomial time reducible to D. So other NP complete problems obtained through this polynomial time reduction from a known NP complete problem can also be taken. For example, like a traveling salesperson, knapsack problem, all these problems we can find out, and we can easily identify it. So whether P is equal to NP, it's you can search some articles based on this, and you can also come up with some research articles where you can say whether your polynomial problem, all the polynomial problem is a non-deterministic polynomial problem also. So what time now? So whenever you have a polynomial time algorithm for just one NP complete problem, we need to discover it, and for that every problem in NP we can say whether it can be solved in the polynomial time or not. So that is nothing but we say that when you say it as the polynomial, we have to say whether it is equal to non-polynomial problems also. So mostly it is not. So we still some research is going on. So you people also can take some articles, download some articles, go through it, and you can come up with your own suggestions or solutions where you will be saying whether P is equal to NP or not. So P, here we are considering P as a proper subset of P, where if P is not equal to NP, then the NP complete problems are not in P. Although many of them are very useful in practice, we are yet to discover all these things. So you can take some bounded algorithms, find out the lower bound, and so here we have seen what is the limitations of the algorithm power. We have seen the lower bounds, how to establish the lower bound by finding the tight lower bound. The establishment is based on trivial lower bounds, information theoretic arguments, adversary arguments, and problem reduction. For each one we have seen with some examples also, and we have all the decision tree is very, very important. You can find any solution by using the decision tree for any given problem, insertion sort or searching. Anything can be done with the help of the discovered with the help of the decision tree also. Okay, so this is all about the limitation of the algorithm power. To cope up with this limitations of the algorithm power, we have two techniques, backtracking and branch and bound, that we will be seeing it in the next class, where in backtracking and branch and bound we are going to solve some problems which is called as the NP hard problem. So far there is no polynomial time algorithm for this. All the algorithms are ending up with an exponential time factor. So if you have any problem which is of the non-polynomial category, then we can consider it as either as the optimization or the decision problem. So mostly the decision problems are solved by using the backtracking technique, and the optimization problems are solved by using the branch and bound technique, where you will be constructing a state space tree. In backtracking we use the DFS or the depth first search. In branch and bound we use the breadth first search. So basically these two techniques are used for coping up the limitations of the algorithm power. So those techniques, how to implement that technique, and some few examples for each one. Some examples are given, like NQ problem, Hamiltonian circuit. It is given for the backtracking method, sum of subset problem, etc., where you can construct a state space tree and go based on the depth of a search. If you take branch and bound technique, we are given with the assignment problem, knapsack problem, and the traveling salesperson problem, and we see how to do it with the help of the breadth first search. So this is what we are going to cover in the next chapter, and I would like to take some problems also. So we will be seeing it, the two techniques with some problems in the next coming class. Okay, thank you.